I haven't posted them yet. I'm posting them kind of one at a time for right now. But they're on YouTube. Yeah. What's that? You mean like the channel? I don't even know if I named the channel. Like I said, I just started doing it. So, yeah. I'll have to look. All right. So, you guys, look. Half of the course is about tangent lines. So, this is the first time you're going to hear about it. I'll be doing a lot with tangent lines today and definitely the rest of the semester and beyond. So, here we go. First of all, you're going to know what I mean when I say tangent line at a point. So, here's the point P, or in other words, the point A comma f of A. And what I did is I drew this tangent line here. Now, a couple of things you need to know about that tangent line. What is a tangent line? A tangent line at the point is a line that touches the graph at that point and has the same slope as the slope of the curve. So, I mean, look at the slope of the tangent line, and doesn't that kind of give you the slope of how the curve is turning there, doesn't it? Okay, so those are the same thing. The slope of the tangent line kind of gives you the slope of the curve is at that point. Okay, now we're going to start out by estimating the slope of the tangent line, and then in a few minutes we'll move into actually finding the exact slope of the tangent line. So let's start out with estimating. How do we estimate the slope of the tangent line? Well, first of all, what I did is I drew a curve for you here. Here's the graph of f of x. And I picked the point on the graph, and I called it point P. There's the point 2 comma 3. And I drew the tangent line. Can everybody see the tangent line there? All right, now I want to talk about finding the slope of that tangent line. Now, to do that, what we need to do is we need to pick another point on the line. So what I did is I picked this other point here like 1, 1. Are you following me? And I connected those 2 points. And so that gave us what we call a secant line. A secant line is a graph that crosses at 2 points on a curve. So by picking a point to the left of P like 1, 1, I drew the secant line, and I just used algebra 1 to find the slope to those 2 points. So I did 3 minus 1 over 2 minus 1, and that gave me 2. And notice I used a wavy equals sign because that is not the exact slope of the tangent line. That's the approximate slope of the tangent line. So again, what I did is I used the slope of the secant line to approximate the slope of the tangent line. What did I do over here, guys? What did I do here? Well, now I picked a different point. This time, I picked a point to the right of P, like 3, 4. Again, I used algebra 1 to find that slope to those 2 points, and I got 1. All right, so what I'm saying is this. If I ever ask you, or the AP test asks you to approximate the slope of a tangent line, all you got to do is take the point and then pick another point nearby to the left or the right and just do algebra 1 and find the slope. So what I'm saying is 2 would be an acceptable answer for the approximate slope of the curve. 1 would be an acceptable answer for the slope of the curve. But what does common sense tell you? Common sense tells you that the real slope you want, the slope of the tangent line, is what? Somewhere what? In between. Because the first time I picked a point to the left of P, the second time I picked a point to the right of P, and so the real slope I want, the real slope of the tangent line, is somewhere in between 1 and 2. Does that make sense? So what's a way I could find a better approximation then? What can I do with the 1 and the 2? I can what? Average them. So I can add them up and divide by 2, and that gives me a better approximation of about 1.5. Does that make sense? All right, so, but again, I want to emphasize that any of those 3 would be an acceptable answer if this were a test question or an AP question. All right. Now let me do another one of these. This time, instead of giving you a graph, I gave you a what? A table. And I want you to approximate the slope of the tangent line at the point 7 comma whatever. So there it is. And so to find the approximate slope of the tangent line, you take that point and another point nearby, maybe like that one, and do change in y over change in x. So what do you get? 26 minus 23 over 7 minus 5, what does that equal? 3 over 2, so it's 1.5. So 1.5 is one approximation. How could I get another approximation for the slope of the tangent line? Well, take that point and a point on the other side nearby. And what's 35 minus 26 over 10 minus 7? What do I get there? Whoops, I'm sorry, 26. So what's 35 minus 26 over 10 minus 7? 3. And so that serves as another approximation. And if you wanted a better approximation, you could do what with those two? Average them, right? Okay, so any of these would be fine. Any questions? All right, now you should be able to apply this then in a real world scenario. Like, for example, suppose we're talking about a tank that's draining out the bottom. Okay, we'll use V for the volume of water in gallons. We'll use T for the time in minutes. And I want you to approximate the slope of the tangent line at the moment in time when time is 15 minutes. Are you ready? So there's the point I want to work at. And so pick any point nearby, like maybe that 10, 54. And I would do, let's see, 34 minus 54 over 15 minus 10, which gives me what? -4. Now, on applications, you've got to put units. What are the units on the 34 and the 54, guys? What are the units? Gallons. And what about the 15 and 10? What are the units on those? Minutes. So what is this? This is the and again, I better put a wavy equal sign. This is the approximate rate at which the water is draining out at time equals 15 minutes. Does that make sense? Okay? Okay, so again, so what you should be thinking of now is that the derivative gives you what? The rate at which something is changing at one point or at one moment in time. Isn't that what a derivative is then? Okay, now that you've seen it in application, that should make sense to you. Okay, so that's where I'm going next then. So when I talk about the derivative of a function at a point, that's the same as not only the slope of the tangent line or slope of the curve, it's also the same as the what? Instantaneous what? Rate of change, right? It's how fast, right? Something's changing at one moment in time, or in this case, and just in general, it's, you know, the instantaneous rate of change of y over the change in x, right? Got it? All right. All right, now, a couple things you got to know, guys. This is how we indicate a derivative. So if you ever want to indicate a derivative, you put like a little quote mark between the f and the a, and that's how you indicate the derivative. And we read that as f prime of a. So f prime of a stands for the derivative, right? Which is the same as the what? Slope of the tangent line, which is the same as the slope of the curve, which is the same as the instantaneous rate of change at a point or at a moment in time. Are you following me, guys? All right, now, guys, what I'm about to do next is derive a formula for the exact slope of the tangent line. What was I doing here? I was only what? Estimating the slope of the tangent line. Well, after a few minutes, after I slowly build up to this formula, in a few minutes we'll have a way to find the exact slope of the tangent line, and that's what we're going to be doing from that point forward. Are you ready? Okay, so watch how I come up with this formula. If you understand where it comes from, you'll not only understand it better, but you'll remember it without having to just memorize something blindly, which is very difficult to do. So anyway, so watch where I get the formula from. Are you ready? Okay, I'm trying to find the tangent line at this point right here, the slope of the tangent line at that point right there. Well, before I go there, here's what I'm going to do. I'm going to pick another point nearby, right here, point Q. And by the way, how did I get that point Q? That's important. Well, what I did is I went over some random distance h here, right? And that gave me a new x value of a plus h, and then I follow that up till it hits the curve, and that gives me the new point Q, which is a plus h, comma, f of a plus h. Do you understand where that comes from? Okay, and then what I'm going to do is I'm going to draw a line through these 2 points. So what I'm going to do now is I'm going to find the slope of that red secant line on the next page. Are you ready? Here we go. Okay, so I drew the secant line like I just explained. All right, guys, how do I find the slope of that secant line? Don't I just do change in y over change in x? So wouldn't I take that y value minus that y value over that x value minus that x value, right? And by the way, in the bottom, what cancels out? The a's. And so I get this. Okay, what is that again? That is the slope of the secant line, right? The one secant line I have drawn there, correct? All right, now, think about it now what we're going to do. What would happen, guys, if I took that point Q there and I started to slide it to here, to here, to here, and so on? What if I started to slide that point Q closer and closer to P? What's going to happen to those secant line slopes? They're going to what? Get closer and closer to the tangent line slope, which is what we want, correct? So that's what I'm going to do now. The question is, how do I force that point Q to get closer and closer to P? By what? By making this distance h what? Smaller and smaller. By making that distance h smaller and smaller, that's going to force Q to get closer and closer to P, isn't it? So that's where this comes from. To make the point Q go to point P, I'm going to make this distance h here smaller and smaller by saying let h go to 0. Are you following me? Okay, now, what is this again? This is the what? Slope of what? One of those secant lines, right? And so what I'm going to do is I'm going to take the limit of those secant line slopes as h goes to 0. And by taking that limit, whatever those secant line slopes are going to will be the what? The exact what? Slope of the secant line. In other words, that will be your derivative value. Is that clear? So again, I didn't want you to just memorize that formula. I wanted you to see where I got it from. Okay, now you are going to eventually have to memorize it, but at least now you know where it comes from. So maybe that'll help you recreate it if you forget what it was, right? Okay, now, again, what does that give you? It gives you the derivative value or slope at one point, which is a comma f of a. Are you following me? All right. Now, by the way, I call this form number what? 1 for the definition of the derivative. So when on the homework tonight or on Wednesday's test, when I say use form 1 of the definition of the derivative to find the slope of the tangent line, that's the formula I want you to use. All right, now I'm going to come up with form 2 for the definition of the derivative. And let me explain where this one comes from. It's very similar. Okay, so here's what I did differently this time. Instead of calling that the point a plus h, f of a plus h, I just called it some other random point x comma f of x on the graph of f of x. Okay? All right, same concept now. I want Q to get closer and closer to P so that the secant line slope will eventually turn into what I want, which is a tangent line slope right here. So how am I going to force point Q this time to get closer to point P? How am I going to force that to happen? Well, all I got to do is make x get closer and closer to what? A. And that'll do it, won't it? If I make x get closer and closer to A, won't that force point Q to get closer and closer to P? Okay, you following me? So how is this going to set up now? I'm going to take the limit as what? As what? X goes to A, as I just explained. And what are you going to be taking the limit of? Well, what are the secant line slopes now using these 2 points? What's the slope of the line through the point x comma f of x and a comma f of a? What's the slope to those 2 points? Well, wouldn't it just be f of x minus f of a over x minus a? Are you following me? Okay? So that's just another way to do it. Just using different variables and a different approach. But essentially, it's the same idea, isn't it? Following me over here? Yeah? Okay. And again, that's going to give you f prime of a, which is the slope of the tangent line. Again, that will give you the derivative value or slope at one point, right? A comma f of a. All right, so let's finally do some examples. This is where you're going to have to start writing stuff down, guys. Ready? And again, write really, really small in here because it's about 4 or 5 of these limit steps. So I'll write really small. Ready? All right, I'm going to use separate paper so I don't have to cram it in there. Okay, here it goes. Okay. So I want to find the derivative or slope of the tangent line for that function at the point 3 comma something. Now I may or may not need the y value, but I might as well find it. What is it? What's the y value there? If I plug the 3 in there, what do I get, guys? 10? Okay. Are you ready? By the way, which form of the definition of derivative does it say to use this time? Form 1. Okay, are you ready? Here it goes. So to find f prime of a, which in this case is f prime of 3, which by the way will be the slope of the tangent line at the point 310 here, you take the limit as what? What is it? H goes to what? 0. And what goes on top here? F of a plus h, right? Which in this case would be f of 3 plus h, and then minus f of a, which is f of 3, right? All over what? H. Everybody agree? Okay, so you should have written that down. All right, and then here we go. Ready, guys? How do I find f of 3 plus h? Well, don't I just plug the 3 plus h right into there for x, right? Okay, and then minus f of 3, which we already figured out was 10 a minute ago, right? All over h. Any questions so far? Okay, by the way, always try substitution. What do I get when I plug a 0 in for h here? What do I get when I put a 0 there and a 0 there? I get 0 over 0, so I'm stuck. Any ideas on how I'm going to get unstuck on this? What should I try? Yeah. Yeah, let's try that. Let's try foiling the 3 plus h and see what happens. Ready? Here we go. So if I FOIL, I get what? 9 plus 6h plus h squared. Now don't lose the plus 1 minus 10. Those are still there. And then all over h. Any questions so far? No? Make sure you get this down so you have something to look at later. All right, what happens now, guys? What happens with the 9 and the plus 1 and the minus 10? Those all add up to what? 0. So they're gone. All right, now that's good because now I can pull what out on top? An h. Let's do that. And that's good because now I can cancel these. And now that I've simplified as much as I can, aren't we supposed to try substitution again and see if we get the limit this time? So what do I get when I put 0 in for h right there? 6. All right. So what is that again? That's the value of f prime of 3. But what is it again? That's the answer to part A. What is that again? That is the what? Slope of the tangent line at the point 3 comma 10 on the original graph, which by the way is the parabola y equals x squared plus 1. Got it? Right? All right, now what does part B ask you for here, guys? Part B asks you for what? The equation of the tangent line. Remember what I say. On the first day in here, I don't want you to start with y equals mx plus b. Instead, I want you to start with what? The point slope formula, right? Okay, so I want you to use that form for the equation of a line to write the equation of the tangent line. So what we know right now is at the point 310, we have a slope of what? 6. Okay. So we're just going to use that point and that slope and write the equation for the tangent line. Real easy now, isn't it? Real easy. So here we go. We get y minus 10 equals m, which is 6, times the quantity x minus 3. Correct? All right, now if you want to, you can now change it to slope-intercept form, so let's go ahead and do that. So I'm going to go ahead and change it to slope-intercept form by distributing the 6 and then adding 10 to both sides. Okay, guys? All right, now hold on. I don't want you to just find stuff without at least pausing for a second and thinking about what we just found. What is that? Y equals 6x minus 8. What is that? That should be the what? Tangent line at the point 310 on the original graph, which, by the way, is a parabola. Isn't the original graph y equals x squared plus 1 just a parabola? Shifted up 1 unit? Okay. So watch this, guys. If I graph the original function, there it is, y equals x squared plus 1, and at the same time, I graph this y equals 6x minus 8, this is what I get. And by the way, I already played around with the window, so this is what I get. There's the original parabola graph, and sure enough, there's a tangent line right there at the point 3, 10, right there. Got it? Good? Any questions? I mean, you got to understand what you're finding. I can't just have you guys finding stuff without knowing what you're finding. Otherwise, it's pointless, right? So, there it is. Any questions? Okay, let's move on then. Let's go to example 4. Again, write small. I didn't give you a whole lot of room. Okay, so what are we doing this time, guys? Well, we've got this function, and we were talking about at the point 4 comma whatever, and might as well find the y value. Guys, what's the y value there if I plug the 4 in there? Quick, what is it, 2? So I want to find the value of the derivative, which is the slope of the tangent line at the point 4, 2 on this graph. Are you ready? So that value would be f prime of 4. And by the way, this time I'm going to use form number what? Yeah, this time it says use form 2. In example 3, we used form 1, didn't we? So now we're going to use form 2 for the definition of the derivative. So make sure you use the right form on tonight's homework as well as on Wednesday's test. Okay, so what's the new form? Well, to find f prime of a, I take the limit as x goes to a, right, of f of x minus f of a. What's f of a here, guys? What's f of a? 2. And then all over x minus your a. Isn't that form 2 for the definition of the derivative? Isn't it? Look at it. Right? Okay, so now all we got to do is find this limit. Okay, what happens when I substitute in the 4? Do I get my answer or am I stuck? I'm stuck. What do I get? 0 over 0 again? So chances are there's going to be some kind of trick when I get 0 over 0, right? To get unstuck. What's the trick here, guys? What's the trick? Yeah, multiply by the conjugate. Very good. All right, now don't make the mistake of foiling in the denominator. Just leave the denominator alone as x minus 4 times square root of x plus 2. Got it? Leave that alone like that. Now on top, I'm going to FOIL. So what do I get when I FOIL that times that, guys? Well, notice, isn't that in the form a minus b times a plus b from Algebra 1? And what did you learn in Algebra 1? When you FOIL a plus b times a minus b, it always FOILs into what, guys? You tell me. A squared minus your b squared. So in this case, it's what? Square root of x squared minus 2 squared, okay? Is that what you get when you FOIL on top? Okay, and so the good news is the square root and square cancel out there. So now I have this. Okay, what happens now, guys? Can I reduce or cancel anything? Yeah, what? X minus 4s. And then I can finish finding this limit by simply replacing the x with a 4 here. So what do I get when I do that? What's my answer here? 1 over 4. And again, what is that? That is the slope of the curve, or slope of the tangent line at the point 42 on the original graph, which is the graph of y equals square root of x. Okay? Now wait, part B wants you to find the what? Equation of the tangent line. So this time we got at the point 42, the slope is 1/4, right? So using the point slope formula, I think you'll all agree that you get y minus 2 equals 1/4 times x minus 4. And then if you wanted to, you could change it to slope-intercept form. Okay? Good, guys? Any questions? Okay, next page then. All right, now, you've heard the saying that you know something well if you know it inside out and backwards, right? Well, it's kind of what I'm getting at here. I think you'll understand those formulas a little bit better if you can follow them backwards as well as forward. So here's what I want you to do. I want you to take this limit, which I'm telling you right now is one of the forms of your derivative, and work backwards and tell me what the original function is and tell me what the original value of a is. Now the first thing you got to figure out is which form does that look more like? Does it look more like form A? I'm sorry. Does it look more like form 1 or form 2? Well, then don't just say form 1 because it has an h in it, because they can use any variable they want on the AP exam. So don't let that be the reasoning for your answer. So if you think it's form 1, why is it form 1? Don't say because it has an h. That's not what I'm looking for. What do you think it looks more like, form 1 or form 2? Well, I'll put them up there again if you want me to. There they are. Which one does it look more like and why? 1. Why? Because of that, it looks like it has an a plus h in it, right? That's the main reason it looks more like form 1. Looks like you got an f of a plus h right there in that first spot on top, right? Do you agree? Okay, so with that in mind, I'm going to go with form 1. Okay, so if it's form 1, then you should be able to work backwards and pick out your function. So guys, this right here isn't that right there your f of a plus h, isn't it? Looks like it. So if that's your f of a plus h, then what are you plugging a plus h into? What function? Look at it. What are you plugging a plus h into? Yeah, square root of x squared plus 5, correct? Do you agree? It looks like you're plugging your a plus h into the square root of x squared plus 5 function. Yep. And if 2 plus h is your a plus h, which we've been saying now it is, then your a has to be what? 2. How can you check that how can you further check that it might be right? Where should that 3 come from? It should come from your f of a. So what's f of 2? What do I get when I plug a 2 into square root of x squared plus 5? Square root of 9, which is 3. Sure enough, it looks like it's right, doesn't it? Right? So double checking, that looks right. Okay. All right, what about B? What does this look like? Form 1 or form 2, you think? Form 2? And if so, then this is supposed to be your f of x, isn't it? Isn't it? And so it's supposed to be f of x minus f of a all over x minus a. So if x is x minus a, then a would have been what? Don't you have to think of the bottom as being x minus 0 to see the a? So the a is what? 0. Because there was only x. Remember, it's got to be x minus a. So clearly your a must have been 0 for there to be nothing there. Do you understand what I just did? Yes? Okay. All right, good. Now we're going to move into something different. Guys, let me ask you a question. All that work we did here on examples 3 and 4, all that got you what? One slope at what? 1 point. So if I wanted you to find 10 slopes at 10 points, do you want to go through this limit stuff 10 times? No, there's a better way, isn't there? Yes, there is. And that's what we're going to next. So here we go. How can I come up with a general derivative function? Well, it's simple. What I'm going to do is I'm going to take form 1, my derivative, right here, and instead of putting in a specific x value a, here, here, and here, I'm just going to leave it as a general variable x. So I'm going to put in x there, I'm going to put in x there, I'm going to put in x there. I'm not going to put in a specific x value. I'm just going to leave it as a variable x. And so watch what my formula turns into. What does that turn into if I put an x there instead of a, an x there instead of a, and a general x there instead of a? Then don't I get this new formula 3? Don't I? Okay, so that looks just like form 1, except now you see an x everywhere there was a specific value a. Okay? All right, and so when I'm done, am I going to get a number or no? No. I'm going to have a what? A formula with what? With x in it. So that's why I call this the derivative function instead of a derivative value. You'll see what I mean in a minute when I do an example. Are you ready? I'll tell you right now. In example 6, you're going to have to write really small right here, and then maybe come over here and continue here. Write really, really small. Okay, here it goes. By the way, guys, I want to find the derivative function f prime of x for this. It's not till the end that I want to use these 3x values. So ignore those 3x values for right now. Ignore them. All I'm going to do is use form 3 of the definition of derivative to come up with my derivative function f prime of x. Are you ready? Okay, here it goes for that function. Okay? Write really small. Okay, so first of all, this is my function. What is it, x cubed plus 2? Okay, so how do I get the derivative function f prime of x? Well, I take the limit as what? H goes to 0 of what? F of, what goes here? F of x plus h, right? Agreed? Okay. So isn't that f of x plus h right there, yes? And then minus, what's supposed to go here? It's supposed to go here. F of x, which I'll put in parentheses because I'm subtracting the whole function, and then all over what? H? Okay? Good? Good? Okay. So now, again, try substitution, guys. What happens when I replace h with 0 there and there? What do I get? I get 0 over 0 again, so I'm stuck. Any idea on how I'm going to get unstuck this time? I'm going to have to what? Expand that. If I expand that, maybe things will start canceling out. Yes? So how do I expand x plus h cubed? Isn't that something I told you on the first day is going to come up every once in a while? And so you got to know how to cube a binomial? There was a little formula. Anyone remember what it is? Who can help me cube x plus h? What do I get when I cube x plus h? Somebody help me. X cubed plus 3x squared h plus 3xh squared, and then plus h cubed. Now, don't lose the plus 2. It's still there. And then here, don't you agree I need to distribute the minus? And then all over h. Any questions so far? Okay. All right. Does anything cancel out now? Yeah, a whole bunch of stuff, right? What cancels out? The x cubes add up to 0. They're gone. The 2's add up to 0. Those are gone. And then you guys, at that point, what can I pull out of those 3 terms? I can pull out a what? An h. So let's do that and see what happens. Okay, so by pulling out an h, I'm now allowed to do what? Cancel the h's. Okay, so after you've done your trick and after you've simplified, then you're supposed to try substitution again. Hopefully this time I'll get my limit, right? So what do I get, guys, now when I substitute in 0 for h? Here and here. What do I get when I put a 0 there and a 0 there? What do I get? 3x squared for my limit. Okay, and there it is, guys. Okay, just like we predicted, we should get a function instead of a number, right? Because we didn't use a specific value x. We just left it as the variable x instead of putting a number in there. Okay, and so there it is. So what is this now? What can I do with this now? I can now use it to find what? Slopes at as many points as I want on the original curve. So it should take you like 2 seconds, right, to plug the x value in there and get a slope. It should take you 2 seconds, right? So here we go. So here's the derivative function I just found. And so, for example, now, if I want to find the slope of the tangent line on the original graph at the point -1 comma something, all I got to do is take the -1 and stick it into there. And what do I get? 3. So what does that mean? That means at the point -1 comma whatever on my original function, f of x, the slope of the tangent line is 3. Got it? All right, do another one. How about at the point 0 comma whatever? Well, if I stick a 0 into here, what do I get? 0. So what does that mean? At the point 0 comma whatever on the graph of f of x, the slope of the tangent line is 0. By the way, what kind of a line has a slope of 0? You learned that in Algebra 1 as well. What kind of a line has a slope of 0? Horizontal. So you would have a horizontal tangent line there. Is that clear? Okay, another one. How about at the point 2 comma something? Plug a 2 into here. What do I get? 12. So what does that mean? At the point 2 comma whatever, on the original graph of the original function, the slope of the tangent line would be 12. The slope of 12 is really steep, so it would have a really steep slope, wouldn't it? Okay? All right, now, all right, so before I go into the last part of my lesson, guys, it's absolutely critical you understand this next box. You have to. If you don't understand this next box, then you're going to completely miss the relationship between f and f prime. Okay, here we go. Let's go back to this example 6. There was the function. There was my derivative function. What happens when I plug -1 into my original function? I get what? The point what? 1, 1. Okay? What happens when I plug -1 into my derivative function? What do I get, guys? 3. So we have the point -1, 3 on the derivative graph, if you were to graph the derivative, right? If you were. Okay, so what does that mean? That means this y value here, the y value on f prime, which is 3, gives you the what? Slope at the point what? -1 comma 1 on the original function. Is that clear? Yes? No, I mean, I'll explain it again up here. What is this value here? What is the value of f prime negative? Well, it's 3. What is that? That's the slope of the curve at the point -1 comma whatever on the original curve. This is the slope at the point 0 comma whatever on the original curve. So once you have your derivative function, the y values on the derivative function graph give you the slopes on the original graph at the same particular x value. Have I made that clear? All right, maybe you'll see it again down here. So what I did is I graphed f of x. There it is, that cubic function I drew there. There's a derivative function, which we should all know is a parabola. 3x squared is a parabola. So when you start picking y values off the parabola graph, what are those y values on the derivative parabola graph? So for example, what is that y value there? Well, that's the y value here at x equals -1, right? So when you look at -1 over here, that 3 should give you the what? The slope of the tangent line there. You see that? Got it? Let's do another one. Let's look at the point where x is 0 right there. Okay, so at x equals 0, what's the y value on the derivative? What is it? What's the y value there? 0. So guess what? That gives you the what? Slope of the tangent line over here at the point 0 comma whatever on the original curve. So again, the y values on the derivative tell you the slopes at those same x values on the original curve. You have to see that relationship, otherwise the rest of the lesson is going to be very, very confusing. Okay? And by the way, does that make sense that I would have a horizontal tangent line there? Does it? Let me explain that. Okay, if I gave you a cubic graph like this, which is a cubic shifted up 2. Okay, so there's the original function. If I asked you to draw the tangent line right there, what kind of line would you have to draw to make the line tangent? Would you have to draw a horizontal line so it only touches at that point? And think about it. Isn't the graph kind of flat there momentarily? So it would make sense that you'd have a flat tangent line. Because what's happening is the graph of f is increasing and it kind of flattens out for a second, then starts increasing again. So does this make sense that you'd have a horizontal tangent line? Yes? It does, doesn't it? Okay, so you should start seeing how all this comes together. And that's what the rest of the lesson is about. So please flip the page. All right. I typed all of this up for you so you don't have to write anything down on this page and I can just fly right through it. But you have to understand it. I'm going to go fast. Please stop me if you don't understand. Ready? Okay. By the way, all these graphs here, I want to point out, these are all f of x. All of these little pieces of the graph I have here, those are all f of x. This is f of x, this is f of x, and so on. Got it? All right. And then what I did is I drew some tangent lines here. So I drew a tangent line there. By the way, let me draw a couple more here. So at that point, the tangent line might look like that. At this point, it might look like that. So do you see how the tangent lines would be above the curve like that? Do you see that? Okay, but anyway, more importantly, what do you notice? F is increasing. And by the way, anytime I talk about a function increasing or decreasing, I'm always talking left to right. So do you agree that that graph right there is increasing? And what do you notice about the tangent line slopes? They're all what? Positive. Same thing here. Isn't F increasing here? And when I draw the tangent lines, like this, or like this, or like this, again, what do you notice? All those little red tangent lines have a what? Positive slope. So again, what I'm saying here in number 1 is whenever f is increasing, the derivative values will be positive, right? Got it? Okay. Number 2. What about when f is decreasing? What do you notice? When f is decreasing, here are your little red tangent lines. They all have a negative slope. So in other words, the derivative values will be negative because the slopes are negative, right? When f is decreasing, same thing here. Isn't f decreasing here? So wherever f is decreasing, the slopes or derivative values should be negative. Do you agree that those slopes are all negative there? Okay, now how about this one? I kind of touched on this a minute ago. But what about at the top of a hill, a bottom of a valley, or here where the f decreases and then decreases again, or f maybe increases then f increases again? At all 4 of those situations, you would draw a what? A horizontal tangent line. In other words, the slope would be what? 0. So the derivative values at all those points are 0, correct? Okay, number 4. Notice what happens here. If I drew a bunch of tangent lines down here, they'd all be positive and they'd start to get steeper and steeper. And eventually, at this turning point here, the tangent line would go what? Vertical, wouldn't it? And then after that, the tangent lines would start to fall again, wouldn't they? They'd start to fall, yes? So you see how there's a gradual increasing slope, vertical slope, and then they start to kind of decrease again. Do you see that? Okay, but what happens at that S curve is what I like to call it. What happens right there at the middle of that S curve? The graph of f goes vertical, which means you have a vertical tangent line, which means you actually have a what? Undefined slope, so you have actually an undefined derivative, don't you? So wherever f has an S-curve, you got to know there's a vertical tangent line, which is an undefined slope, which means you don't have a derivative value there. There's no derivative. There's no slope. Right? We all know from Algebra 1 that a vertical line has an undefined slope. Do you remember that? Okay. Now here's the tricky part, number 5. What's happening there? By the way, I call these sharp turns, but why are those sharp turns? I mean, there's a turn here, right? Those are turns. And that kind of a turn, you had a zero slope or zero derivative. This kind of turn, you had a vertical tangent line, right? What kind of turns are these? Well, let me talk about them. What are the slopes at these points? They're all the same. Maybe they're 1, maybe positive 1 or something like that. Aren't those slopes all like maybe positive 1, for example? Then what happens suddenly at that point? Now all these slopes become what? Maybe like negative 1 or something like that? See how there's a sudden change from a positive to a negative slope? See that? Anytime you have a sudden change like that from positive to negative slopes, you can't even draw a tangent line. You can't. Because it's too sudden of a change. But that sudden change means right there the slope is what? Undefined. Same thing here. What's happening here? Well, you got all these positive slopes down here, then all of a sudden, boom, they become negative suddenly at that point. So again, that's a sharp turn. There's a sudden change in slope, and therefore there's no slope. In other words, the derivative is undefined at that sharp turn. Do you understand that? So these are your 3 situations here where you can have an undefined slope. The only difference is here you can actually draw the vertical tangent line. Here you cannot draw a tangent line at all. Got that? Okay, now. Okay, I need to go through the rest of these. Please watch and listen. Some of these might be common sense, but you definitely need to know them before I turn the page. Number 6, what does it say? If f is not continuous, then automatically the derivative is what? Undefined. Number 7, when the derivative is undefined, we have a term for that. What is it? We say the function is what? Not differentiable. Got it? Number 8, if a function is differentiable, then common sense tells you what? It must have been what? Continuous in the first place. So that might be common sense to you, right? Got it? I mean, if you have a derivative, it must have been continuous in the first place. Now this one, please read with me. If a function f is continuous, does that guarantee it has a derivative? No. You just saw 3 examples right there where it might be continuous, right? Isn't f continuous here, here, and here, isn't it? But is f differentiable there? In other words, is there a derivative value there? No. So just because f is continuous at an x value does not guarantee that it's differentiable. Understand that? So it works one way, but not the other. If it's differentiable at an x value, then common sense tells you it was continuous there, right, in the first place. But it doesn't work the other way. Just because it is continuous does not guarantee that it's differentiable. Got it? So it works one way, but not the other. All right. Look at this box here, guys. What is this? These are just different ways you're going to see the derivative written in my notes and in the textbook. You've seen that today quite often. Get used to that way. Just you can sometimes write it as y prime. If you write your equation in y equals form instead of f of x equals form, then you can just put that little derivative symbol on there and call that y prime. That's the derivative. This is also the derivative. If you think about it, what is a derivative again? It's an instantaneous change in y over change in x. Okay, so when you write dy over dx, you can think of that as kind of like change in y over change in x. Or in other words, you can read that as the derivative of y with respect to what? X. And by the way, unless I tell you otherwise, we're always differentiating with respect to what? X. Here's another way you might see it written. Another way, this just means you're taking the derivative of whatever follows in brackets with respect to x. Okay, so the 4 that I circled are the most common ways you're going to see it written, but some textbooks you'll see it written like that as well. Okay? But again, these 3 and this one are the ones you're going to see me write it for the most part in my notes. Okay? All right. Now, I said this earlier in the hour, and I'm going to say it one more time because it's that important before we go to the last page. Are you ready? When I talk about the derivative at a point, it means all of the following. It's the same as what? The slope of the tangent line at that point. It's the same as the slope of the graph or the curve at that point. And it's the same as the instantaneous rate of change at that point. Are you with me? Okay, so all of those are interchangeable. They all mean the same thing. Okay, last page. You guys, I'm going to do one application here, and then there might be one or two on your homework and one or two on Wednesday's test. Please listen closely. Suppose I give meaning now to the function f of x. So suppose I say, let f of x be the position function for a moving object. Well, just so you know, when I do talk about the position function, instead of using f, I use s. And since position is usually a function of time, instead of using x, I use what? T. So instead of talking about the function f of x, I'm now going to talk about the function s of t. And by the way, since s is position, suppose s of t is in feet. And since t is time, suppose t is in seconds, for example. Are you ready? Here it goes. What will be the units on the derivative? Well, what will be the units on the y values s? What will be the units on the y value s? Come on. Feet. What will be the units on the x values t? Seconds. And so when you're done doing this, which I'll go through with you in a minute, what will the units on top be? Feet. What will the units on the bottom be? Seconds. But what is feet per second? That's how fast something's moving, isn't it? So when you take the derivative of the position function, you end up with the velocity function. Velocity is, right, how fast something's moving, right? So what you need to get out of that is that the derivative of the position function will be the velocity function. And by the way, how will you find it? How will you find the velocity function v of t? By differentiating the what? Position function. So if I use formula number 1 for the definition of derivative, I'm going to have the limit as h goes to 0. Instead of f of x plus h, what am I going to have here? Instead of f of x plus h, I'll have what? S of t plus h minus, normally I would have f of x there, but now I'm going to have what? S of t instead of f of x, and then all over h. Are you following me? I'm not going to go through that, but that's what you would need to do then to find the velocity function for a moving object. Okay, last example. It'll only take a few minutes. It's a matching problem. So here's what I want you to do. I want you to look at the graphs of f of x here. There are 4 f of x graphs, and I want you to one by one match them with one of these derivative graphs. So this is a matching question. In order to do this correctly, and you will have some of these on homework as well as on Wednesday's test, what will you need to do, guys? Well, you'll need to start thinking back to this page. Remember when I went through all these, where f is increasing, the derivative should be what? Positive, and so on. So I kind of summarized them again for you here. Let's just read through them real quick. Number 1, guys, for x values where f of x is flat, the derivative should be what? 0. In other words, the y values on the derivative should be on the x-axis, correct? Number 2, for x values where f is increasing, you'd expect the derivative y values to be what? Positive, right? Or above the x-axis. Number 3, for x values where f is decreasing, you'd expect the derivative values, the y values on the derivative, to be what? Negative, which graphically means that the y values would have to be below the x-axis, right? How about for x values when f is not continuous? Then you would expect f prime to be what? Undefined, right? Got it? And finally, what about for x values where f is vertical or has a sharp turn? Again, you'd expect f prime to be what again? Undefined. Got it? Okay, so here it goes. With all that in mind, we are now going to match. Okay, so let's look at graph Roman numeral 1. What do you notice here at x equals 0? You'd have a what? Horizontal tangent line, right? So the graph of the derivative should have a y value of what? What's the slope there? At x equals 0, do you agree the slope is 0 because you have a horizontal tangent? So you'd expect the y value there to be what? 0, which it is. You'd expect the y value to be 0. Aren't all these 0? So did that help looking at that? No. All right, so let's look at some other x values. What about, for example, at these 3 x values here? Well, if I drew tangent lines there, what do you notice? The slopes are all what? Well, let's just look at them in general. They're all negative. So on your derivative graph, here, here, and here, 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 and here, 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 and here, 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 and here, you'd expect the y values all to be what? Negative. Remember, the y values here are the slopes from here. So if those 3 slopes are negative, then the 3 y values here better be negative. Are these 3 y values negative? No. So it's not that one. Are these 3 y values negative? Yes, so it might be B. Are these 3 y values negative? No. Are these 3 y values negative? No. So what is it, guys? It's what? B. So you agree that 1 matches with B? You want to look further? Let me prove it to you further. What about it? Maybe these 3 x values here. The slope there, there, and there would be what? Positive. So you'd expect that these 3 x values there for these y values to be positive. And sure enough, they are. Because the y values here are the slopes from here. You understanding the relationship here? Okay, let's do another one. Let's look at this one. Roman numeral 3. Well, let's look at the hills and valleys. Do you agree the slope there is 0, the slope there is 0, the slope there is 0, the slope there is 0? Do you agree with that? So at this x value, this x value, this x value, and this x value, you'd expect the y values over here to be what? 0. Well, sure enough, that would be here, 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 and here. At all 4 of those x values, is the y value 0 here? Yes. Remember, the y values here, which are all 0, give you the slopes here, 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 and here, which are all 0. See how those slopes are all 0 there? So do you agree that that goes with D? Are you following me here? I mean, you can look in between if you want, but it's all going to fit, right? All right, let's do another one. Let's look at, let me pick a different color here. Okay, how about blue or purple here? Let's do purple. What do you notice at these 3 x values here? The slopes would be what? Positive, yes? What about at these 3 points here? The slopes are all what? Positive. So you'd expect the derivative graph to have all positive y values here, here, and here, and here, here, and here. So that's got to be what? A. You see how at these 3 y values, at these 3 x values here, these y values are positive? Same thing at these 3 x values here. Aren't these y values all positive? Aren't they? Because the y values here are the slopes from here. See how they match? Do you agree that's A? All right, and let's finally look at Roman numeral 4. All right, what do you notice here, here, and here? You'd have a slope of what? 0, a slope of 0, and a slope of 0, right? Wouldn't you have horizontal tangent lines at all 3 of those x values? What are those 3 slopes? 0. So you'd expect here, here, and here to have a y value of 0 on the derivative. Do you have a y value of 0 there, there, and there? Yes, you do. So that's what? C. Got it, guys? Can you do this? Okay, good.